I see this as the title highlighting the core topic: how the alpha parameter influences the LassoLars regression model. LassoLars is a specific type of regression that uses the least angle regression, LARS, algorithm, which I'll explain later. This sets the stage. We're focusing on the alpha parameter within the LassoLars algorithm. My goal is to understand how changing alpha impacts the model. I'm breaking this down into steps for you. First, I review lasso regression basics. Then I'll explain the LassoLars method, and finally, I'll analyze how alpha affects the model. This step-by-step approach will make things clearer. We need to understand lasso regression, a type of regression that adds a penalty to the model, and its connection to regularization, a technique to prevent overfitting. We will also use our understanding of how LassoLars works. This problem is theoretical, so no calculations are needed. A larger alpha value means a stronger penalty on the size of coefficients, resulting in more of them being set to 0. This simplifies the model. A smaller alpha weakens the penalty, which allows the model to fit the training data more closely. But be cautious. This might lead to overfitting. If alpha is 0, there's no penalty, meaning it becomes a regular ordinary least squares, OLS, regression. This is important because OLS regression doesn't do any regularization. Alpha directly controls the strength of the L1 penalty in the lasso regression. This is the key to understanding the model's behavior. Alpha is the main control knob. I see alpha as the dial controlling the L1 penalty's intensity in LassoLars regression. A higher alpha cranks up the penalty, forcing the model to use fewer features, while a lower alpha softens the penalty, letting the model use more features. This penalty discourages the model from overly relying on any single feature. Think of it like a tax on complexity. The alpha parameter directly impacts the model's complexity. A higher alpha means a simpler model with fewer features because the stronger penalty forces many coefficients to 0. A lower alpha leads to a more complex model because the weaker penalty allows for more features to be used. Imagine a Lego castle. Higher alpha is a smaller, simpler structure, while lower alpha is a large, intricate one. I interpret alpha as affecting how well the model fits the training data. With a higher alpha value, I get a simpler model that sacrifices some data fitting accuracy for better generalization. A lower alpha value gets me a more complex model that fits the training data much more closely. This increased fit is tempting, but beware. I may overfit and perform poorly on new, unseen data. Think of it like fitting a curve to points, where alpha affects how tightly I hug those points. I've seen how these factors interact beautifully. A higher alpha translates to a stronger L1 penalty, resulting in a simpler model that may not fit the training data as well. A lower alpha brings a weaker penalty, a more complex model, and a tighter fit to the training data. And if alpha equals 0, then the penalty disappears, and I end up with a plain old ordinary least squares, OLS, regression model. This shows the direct relationship between a high alpha and the effects on L1 penalty, model complexity, and data fit. I find it pretty intuitive that stronger penalties generate simpler models, which in turn lead to less precise fits to the training data. This shows the opposite end of the spectrum. When the alpha is lower, the L1 penalty is weakened. This results in more complex models that fit the training data more closely. I have to be careful with this, though, as it could lead to overfitting. Setting alpha to 0 effectively eliminates the L1 penalty, simplifying LassoLars regression to ordinary least squares, OLS, regression. OLS is a basic linear regression method that doesn't perform regularization. I'm going to explain the crucial role of the asterisk alpha parameter in the LassoLars regression model. LassoLars uses a technique called least angle regression, LARS, to efficiently solve the lasso problem. The core idea is that alpha controls the strength of regularization, impacting how much the model simplifies itself and prevents overfitting. This question tests your understanding of how the alpha parameter influences a LassoLars model. We'll analyze several statements to determine their accuracy based on how alpha affects model complexity and its fit to the data. Absolutely. The alpha parameter directly scales the L1 penalty term. This penalty term shrinks coefficients towards zero. A larger alpha means a stronger penalty, leading to more coefficients becoming zero, and creating a simpler model. Think of it like a knob. Turning the knob, increasing alpha asterisk, increases the penalty. When alpha is zero, there's no penalty. This means it's equivalent to ordinary least squares, OLS, regression. OLS is a method that aims to minimize the sum of squared differences between predicted and actual values. It doesn't perform regularization and can easily overfit, particularly with datasets having many variables. With a smaller alpha asterisk, the penalty is weaker. This means the model can more closely fit the training data. However, this closeness to the training data can come at the cost of potentially overfitting, where the model might perform poorly on new, unseen data. You got it. A larger alpha imposes a stronger penalty. This forces more coefficients to shrink to exactly zero, feature selection. The result is a simpler model with fewer features used in making predictions. This helps reduce complexity and the chance of overfitting. I understand LassoLars as a specific algorithm in scikit-learn that uses the least angle regression, LARS, method to solve lasso regression problems. Lasso regression, in a nutshell, aims to find the best fitting line while keeping the complexity of the line under control. The alpha parameter in LassoLars is a crucial control knob that determines how much emphasis we place on model simplicity versus how well the model fits the data. Think of it like a dial. Turning alpha up encourages a simpler model that generalizes well, while turning it down lets the model fit the training data more closely, at the risk of overfitting. L1 penalty is a type of regularization. Regularization means we add an extra term to the standard error calculations. In L1, we add a penalty that is proportional to the sum of the absolute values of the model's coefficients. A bigger alpha value means a stronger L1 penalty, forcing the coefficients to be closer to zero. Model complexity refers to how many features are actively used in the model. A simpler model uses fewer features, and tends to generalize better to unseen data. This is important in avoiding overfitting, which happens when a model is too closely tuned to the training data and performs poorly on new data. I see alpha as the dial that controls how strongly lasso regression penalizes large coefficients. A larger alpha means a stronger penalty, leading to simpler models by shrinking many coefficients to exactly zero. The L1 penalty is a type of regularization in lasso regression that adds a penalty based on the absolute value of the coefficients. Alpha directly multiplies this penalty term in the equation that lasso regression is trying to solve. A higher alpha increases this penalty, making the model simpler, while a lower alpha allows for more complex models. Let's say you increase alpha. This cranks up the penalty, forcing lasso to shrink coefficients towards zero more aggressively. The result? A simpler model with fewer features. Now, if I decrease alpha, the penalty weakens. Lasso can now afford to have larger coefficients, leading to a model that better fits the training data. However, this can make the model more prone to overfitting. When alpha equals zero, there is no penalty term at all. This means lasso regression reduces to ordinary least squares, OLS, regression, which doesn't have built-in regularization to prevent overfitting. This is the core question of the quiz. It tests whether you understand the role of the alpha parameter in the LassoLars algorithm, which is just a specific implementation of lasso regression. I see alpha as the tuning knob for LassoLars regression. It directly controls how strongly the model penalizes large coefficients. Think of it like this. A higher alpha value makes the model favor simplicity, while a lower alpha allows for more complex fits to the data. Let's break down L1 penalty. It's a type of regularization that shrinks the coefficients towards zero. Alpha directly multiplies this penalty term. A larger alpha means a stronger push toward zero, resulting in a simpler, more sparse model, fewer non-zero coefficients. A smaller alpha weakens this push, allowing for more complexity. Pretty cool, huh? A larger alpha cranks up the L1 penalty. This forces many coefficients to become exactly zero. The result? A simpler model with fewer features actively influencing the predictions. It's like a Marie Kondo method for coefficients. Conversely, a smaller alpha eases up on the penalty. The model is freer to fit the training data closely. This can be awesome, but also risky. A close fit to the training data might mean overfitting, performing really well on the training data, but poorly on unseen data. This is the question you're trying to answer about the alpha parameter in the LassoLars regression model from Sklearn. The goal here is to identify the correct statements about how the alpha parameter affects the LassoLars model in Sklearn. This highlights the importance of understanding the alpha parameter, which is the main focus of the quiz question. This explains the topic of the quiz, exploring how the alpha parameter impacts LassoLars regression. We'll be looking at how different alpha values affect the model's complexity and its fit to the data. This question tests your understanding of the ALPHA parameter in LassoLars regression. I'll guide you through how the ALPHA parameter affects the model's complexity and its relationship to the training data. We'll analyze each statement to determine its accuracy. A larger ALPHA increases the penalty for having large coefficients. This forces the model to shrink more coefficients to exactly 0, resulting in a simpler model with fewer features. A smaller ALPHA weakens the penalty, allowing the model to closely fit the training data. However, this increases the risk of overfitting, where the model performs well on the training data but poorly on unseen data. When ALPHA is 0, there is no penalty for large coefficients. That's exactly what ordinary least squares, OLS, regression does. It finds the coefficients that minimize the sum of squared errors without any regularization. ALPHA directly controls the strength of the L1 penalty, lasso penalty. A higher ALPHA means a stronger penalty, shrinking coefficients towards 0. A lower ALPHA weakens the penalty. The ALPHA parameter is a hyperparameter in lasso regression that controls the strength of the L1 regularization. It determines the balance between fitting the training data and keeping the model simple to prevent overfitting. Regression is a supervised machine learning task where you predict a continuous target variable based on input features. LassoLars is a type of regression model that uses both the lasso regularization technique and the least angle regression, LARS, algorithm to efficiently find the regression coefficients. After training a regression model like LassoLars, you use it to make predictions on new, unseen data. The model uses the learned coefficients and input features to estimate the target variable. This section introduces the scenario, using LassoLars for regression with a high-dimensional dataset and potential multicollinearity. The goal is to understand how the alpha parameter helps address overfitting in this context. This title highlights the core topic of the quiz, understanding the role of the ALPHA parameter within the LassoLars regression model. It helps focus your attention on the relationship between ALPHA and model behavior. LassoLars combines the lasso regression technique with the least angle regression, LARS, algorithm. This means it adds an L1 penalty to its cost function and then uses LARS to efficiently compute the solution path, coefficients, for different ALPHA values.